Welcome and thank you for joining us for today's webcast, Thermal Storage and Management Using Phase Change Material, sponsored by Advanced Cooling Technologies and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation, and those questions not addressed during the live event will be answered after the webcast. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speakers. Brian Musica worked as Research and Development Engineer for ACT's Aerospace Group before taking on a business development role. Brian is currently Sales Manager for ACT's Electronics Products Group, responsible for military and aerospace products. Brian has firsthand experience designing, analyzing, and integrating heat pipes into real-world applications. Also on the line for our Q&A today is Jens Wyant, Lead Product Development Engineer for ACT's Electronics Products Group. During his time at ACT, Jens has contributed to thermal solutions for radar, power electronics, rotating equipment, and other high-power electronics, many of which include heat pipe embedded solutions. He has served as PI on several small business innovation research programs, including a DARPA-funded program focused on laser diode microchannel coolers, a DOE-funded program on passivation coatings for high-power RF loads, and an Army-funded program to develop a liquid cold spray system. So now I'd like to hand the webcast over to our first speaker, Brian Musica. Brian?
Thanks, Billy, and thanks everyone for joining us today. We'll go ahead and jump right in. The goal of today's webinar is to provide viewers with an understanding of phase change materials and certain design aspects to consider when attempting to utilize the unique characteristics of a PCM. We'll start today's webinar with a general overview of phase change material, including how it functions, common PCMs that are used in defense and industrial applications, and what types of systems utilize PCM technology. From there, we'll dive a little more into the design considerations and examples of both standalone PCM heat sinks as well as PCM heat exchangers. So, as is probably obvious by the name, PCMs operate using a phase change, in most cases solid to liquid phase change. During this phase transition, the material's latent heat increases dramatically, which allows it to store thermal energy for a given period of time. The large benefit of integrating PCM into your solution is that it will maintain a temperature during the melt phase. The length of time the PCM can hold the heat is dependent on the volume of the PCM and the power that is being applied to the PCM. So there are several factors that need to be considered when selecting a good phase change material. An ideal solution will have a high heat of fusion, high thermal conductivity, high specific heat and density, long-term reliability during repeated cycling, and dependable freezing behavior. Here listed on this slide are several classes of phase change materials that are seen throughout industry. Paraffin waxes are the most common because they have a high heat of fusion per unit weight. The chemical composition can be altered to allow for large melting point selection. They provide dependable cycling and are also non-corrosive and chemically inert. When designing with paraffin PCM, void management is important due to volume change from solid to liquid. Paraffin PCMs also have a low thermal conductivity, so designing sufficient conduction paths is another key design consideration that we'll get into a little later in the slide package. The next choice is hydrated salts. These PCMs have a high heat of fusion per unit weight and volume, and they also have a relatively high thermal conductivity for nonmetals. They, unlike the paraffins, they show small volume changes between solid and liquid phases, but they are less commonly used in industry because they are corrosive with metal and there is limited long-term reliability data. Other PCM materials are such things as metallics or non-paraffin organics and liquid to gas phase change material. Metallics generally have a low heat of fusion per unit weight, high heat, but they offer high thermal conductivities. Non-paraffin organic PCMs can be flammable and toxic, but do have high heats of fusion. Liquid to vapor phase transitions can also be used to store energy in lower volumes, but do require venting if you're using them as a solution. Since paraffin is the most suitable PCM for most designs, this slide represents a few typical examples. Again, paraffins are preferred because they are chemically compatible with metals. They have large latent heat and can be customized for a large operating temperature range. The list of paraffins shown here are suitable to melt prior to typical electronics max temperature and make it easy to maintain those maximum temperatures during the melt phase. So now here's some considerations for when to use PCM. For military and industrial use, there are three common challenges that PCM can solve. The first is simple heat storage. If your system is a one-time use, such as a missile, the PCM can be used as a standalone heat sink. When designed properly, it can maintain temperature below electronics failure temperature throughout the entire mission. The PCM volume is determined by a combination of the maximum mission duration and power it must store. Oftentimes, a PCM solution can greatly reduce the complexity and increase the reliability by eliminating the need for active cooling. In cases utilizing liquid cooling as the ultimate heat sink, the PCM heat sink can eliminate the need for a cold plate, pumps, valves, and other additional items, which can really increase reliability. The second type of application is for protection against momentary failure. In this case, there is a primary coolant loop, but reliability issues or potential power loss causes the need for a secondary system to avoid failure during that momentary issue. In this case, while the primary coolant is functioning, the PCM module will be in solid state. And when the coolant is lost, the PCM will absorb the heat and melt and substitute for the primary while the primary system reboots. This type of system has very similar design considerations as the one-time use application, and those we'll get into as standalone heat sinks. The final application is for a heat source with a pulsed or duty cycle operation. In this case, the PCM is used as a heat exchanger that dampens the high peak loads and allows the ultimate heat sink to be designed for average heat load. This application typically provides significant weight and volume reductions for those systems operating in pulse mode. So in this next section, we'll look at design considerations for the first two cases, those being the PCM heat sink modules. These modules are sealed, leak-tight units, and the internal design is critical to operation, as we'll get into. So we'll touch on things like optimizing the fins for proper melting of the PCM, as well as void and pressure considerations, and we'll show you some comparisons of tested PCM modules versus theoretical data. So the first step in the design is fairly straightforward. You use your power and time requirements to determine the volume of PCM required. From there, two primary challenges arise associated with the design of PCM module. The first is designing around the poor thermal conductivity of a PCM. As we talked about paraffins being the first option, they typically have thermal conductivities between 0.2 and 0.3 watts per meter K. So simply filling a container with this type of material and applying a heat load will create very large temperature gradients as the PCM melts. The second challenge is avoiding voids at the location of critical heat loads. So you can see in the figure to the right, a void volume is present to allow for the expansion of PCM during phase transition. In most cases, when orientation with respect to gravity varies, the location of the PCM when it melts and freezes will also vary. So if there's significant empty space around a critical component, that component can see large temperature rise before the PCM absorbs the entire heat load. The solution of both these challenges is mainly in the internal design of the conduction paths, and these conduction paths are typically metallic fins. As you see by the thermal resistance network outlined in the figure, conduction through the fins will play a large role in assuring that the PCM melts without significant temperature rise. When you consider that the thermal conductivity of of a metal such as aluminum is around 167 watts per meter K, and the conductivity of the PCM is less than 1, it is really critical to have these metal conduction paths to help your heat spreading. Things to consider are the fin spacing or fin pitch, the thickness of the fins, and going on to the next slide, we'll show you some of the trade-offs that are involved when designing here. So since I mentioned most PCMs are paraffin-based, getting the heat into the PCM efficiently is the key design parameter. This plot is showing the starting point for fin pitch and thickness within a PCM heat sink. The solid line shown increasing to the left side, it shows the time to melt or the thermal storage capacity for a given power, and that is measured on the left axis. The matching colored dashed line is corresponding to the thermal gradient through the fin and the PCM, and that's measured as far as delta T on the right axis. Both curves are a function of fin spacing, so as you can see, there's a trade-off between thermal storage capacity and delta T. As you add more fins, you improve the thermal gradient, but displace more PCM, which reduces thermal storage. A scenario with too few fins is shown toward the left side of the plot. At the other extreme, the spacing between fins is large to maximize the volume of PCM, but thermal gradients are large due to the poor thermal conductivity of PCM. So this occurs toward the right side of the plot. For the heat load and geometry used to generate these curves, the optimum fin spacing is between 0.05 and 0.1 inches, and you can see that kind of towards the center of the plot. This is where marginal gains in thermal storage capacity are observed as fin pitch is increased. So optimizing the fin pitch and thickness assures that all PCM is melted with a minimum thermal gradient, thereby maximizing the performance of the heat sink. So during manufacturing, a heat sink module will be completely leak tight, which makes it a pressure vessel. As we touched on before, since there is expansion going from a solid to liquid, the unit requires a void volume when in solid state. One of the challenges we identified was assuring that the void volume does not cause unwanted temperature rise. And fortunately, this design is negated by proper fin design that we discussed in the last slide. Since the fins will provide a good conduction path to the heat into the PCM, the temperature rise is minimal, no matter if there is a small void at the large heat-generating components. The final consideration is to make sure that your pressure vessel will function and maintain structural integrity at maximum pressure. You can use the ideal gas law to determine pressure of the compressed gas and determine your enclosure material and wall thickness appropriately. So after selecting your PCM, determining the required volume, and designing your enclosure with the proper fin and wall structure, it's time to manufacture and test your PCM. So this slide shows a tested sample with material properties shown to the left. One thing to note is that you can see that the specific heat jumps during the melt phase, in this case between 72.2 and 75.9 degrees C. In this test set, we applied power to one surface and measured temperature at that surface. So due to the PCM we selected, you can expect temperature rise to stall around the 72 degrees C range. So in this slide, we're showing that test result, and if you're familiar with the PCM, with PCMs from past experience, the theoretical line probably looks familiar from things you've seen in the literature. So basically, the theoretical line predicts that the module will heat up until it reaches the PCM melt temperature. It will then hold within a few degrees of that temperature until nearly 100% of the PCM is melted. And once all the PCM is melted, the temperature begins to rise at a similar rate. In this case, the PCM heat sink was designed to absorb heat load for about 250 seconds with margin. And when we tested, you could see the actual curve there matched fairly well and actually maintained under the theoretical temperature throughout the entire test. So now in the next section, we'll look at PCM heat exchangers, and these again are used to dampen high heat loads in pulse devices. So the concept here is that the PCM exchanges heat directly from components or from a primary cooling system to the ultimate heat sink. PCM can store the thermal energy and slowly release it into the ultimate heat sink, which allows you to size that heat sink for average and not peak load. No matter what the source or sink conditions are, if you're operating in a duty cycle PCM, if you're operating in a duty cycle, PCM can help dampen the requirements of your heat sink. Some examples where this can be utilized is reducing the amount of radiative surface required to reject heat in space applications, reducing the convection heat sink volume used in air-cooled applications, or one common solution that we're going to touch on in the subsequent slides is reducing the size of a vapor compression system in a two-fluid heat exchanger. As you can see on this slide, the figure shown here just gives you an example of a pulse load operating on a duty cycle and the average load that the vapor compression system in this case would have to reject. So where this is typically used is, or one application that's typically used in is directed energy weapons. But again, it's applicable anywhere that operates with a pulse mode. So in this example, the duty cycle is typically less than 40%, which should allow for mass reductions in the vapor compression system. The schematic in the bottom corner represents a sampled directed energy system. In this case, the high-energy lasers were cooled with a deionized water loop and is rejected through a vapor compression loop with an air-cooled condenser. The PCM heat exchanger couples and transfers heat between the loops while dampening the pulse loads from the high-energy lasers. So design considerations for this system are similar to heatsink modules, where you'll determine the volume of PCM required to absorb the power over the duty cycle and design the system with enough PCM surface contact in order to reduce conduction gradients through the PCM itself. So the PCM heat exchanger can accomplish this goal by having thin layers of PCM sandwiched in between parallel flows of the deionized water and the refrigerant. The vapor compression system operates continuously but is only sized for average heat load since the PCM balances the peak loads from these layers can be added as needed depending on the PCM volume required. So in the figure to the bottom right, we determined the savings for a given system operating around a 33% duty cycle. This analysis used off-the-shelf components outside of the PCM heat exchanger. The weight of the compressor and condenser are significantly reduced, as you can see there. And although you add weight for the PCM enclosure itself, the mass of the entire system is reduced by a great deal, in this case over 50%. And we have demonstrated this technology and built subscale units up to about 25 kilowatts capacity. So because we have a lot of experience designing these PCM heat exchangers, we've developed a lot of analytical tools to help during the design phase. What we're going to show here is a video that illustrates some of the capability we've inherited and shows the melting and freezing associated with one channel of that flat plate heat exchanger. So as you'll see as the video is launched, the PCM quickly absorbs the pulse load, it melts, and then balances the hot and cold so that it exposes average heat load to the cold coolant. Once the pulse is gone, or the device is on the off mode, the PCM will refreeze and that melt film will push back. So with that video, we're kind of wrapping up our session today. Just going on over some of the key takeaways that we hope you learned and got out of this is that PCM can be used as an effective way to store thermal energy or size your heat sink to average power for pulse mode operation. The PCM selection and volume is dependent on the component operating conditions and boundary conditions of your system, primarily power and duration. And finally, that the internal design of these systems is critical to their performance. And the two big design considerations are proper conduction paths to and from the PCM to avoid the poor thermal conductivity of the PCM itself, and designing the module for appropriate internal pressure. And with that, we want to thank you for joining us today, and we'd be happy to take a couple of your questions.
Brian, at this time, we'd like to begin our Q&A. So if you have a question up there, you can submit it by entering it in the box at the bottom of your screen. And for the Q&A, I'd also like to welcome ACT lead engineer Jens Wyant to the line. We already have plenty of questions here. The first question we have, this attendee writes, I'm looking to keep about 250 grams of a medication around 5 to 10 degrees Celsius. I expect it to be in an insulated pouch carried by the patient. Are PCMs a useful solution to this?
Sure. I think PCMs can be used in this application. One thing to keep in mind is that PCMs are used to store energy. So as long as the PCM is chilled ahead of time, it can absorb that heat load until it is fully melted. So if you pull it out and leave it sit in ambient air temperatures, which are around 25 C, it will eventually melt and no longer be able to store any heat. But it is a repeatable cycle, so you can freeze it and thaw it many times, so it can be reused.
An early slide referred to common PCMs. Why are the PCMs considered common?
So this one ties somewhat closely to the last question. You definitely want to choose a PCM that melts above your ambient temperature in many cases. If you choose one that is within your ambient temperature range, it's going to melt before you actually need it. So the ones on slide 5 are within the range above most common environmental temperatures, but also below many electronics temperatures. That way that they are solid when you need them, but they melt before you reach a maximum temperature.
What happens when the heat input is on the void side?
This goes back to the few slides Brian had about the internal design. The internal fin structures are very important for getting the heat into the phase change material. So when designed properly, the fins are moving the heat to that phase change material. And the void is not that critical. And many times you don't notice any performance difference with respect to orientation, meaning that the void isn't that big of a factor.
Here's another question. What can be done to manage the internal pressure of the heatsink through the phase change?
So there are a few different techniques that can be used for this one. In many cases, these heat sinks are vacuum braced together, and the fins bridge the top and the bottom of the heat sink. So these fins do two things. One, conduct heat into the PCM. Secondly, they act as a structural member holding the PCM heat sink together. So when you go through the solid to liquid phase change, the internal pressure increases, but you have enough structural strength inside to maintain it and keep it as a pressure vessel. Alternatively, the heat sinks can be sealed at the maximum temperature so that the volume inside the heat sink is at its maximum condition. Once it cools down, it'll be under vacuum on the inside, and the highest it'll ever see is about 1 atmosphere.
We have a question here. What is the melting temperature for the PCM heat exchanger?
Again, this goes back to the design requirements. In some cases, the heat exchangers need to operate at relatively low temperatures around room temperature. So waxes in the 20 to 30 C range may be used. In other applications where the evaporative side of your vapor compression system works hotter, you can choose a higher melting temperature PCM. That is one of the nice things about choosing a paraffin wax. There is a very broad range of melt temperatures from about 5 below C up to almost 80 C and above.
Have you studied the effectiveness of PCMs in a reduced gravity environment?
We have not, but the PCMs inside, I think that goes back to the void management question. With the proper internal fin structure, you don't really care where that void is. And many times these heat sinks are charged under vacuum, and it's sealed within the hermetic heat sink itself. So in space environments, we expect them to operate the same.
How effective are small encapsulated paraffins compared with bulk paraffins, and how do they differ in efficiency?
So this also goes back to what Brian was discussing with getting the heat into the PCM. If you have a large volume or a bulk PCM, you typically see large conduction gradients. In the smaller encapsulated ones, you have a much better surface area to volume ratio. So you're able to melt those with a much smaller gradient. It's also a trade-off of your total volume, which affects your heat storage capacity.
Here's another question. If we use a stainless bellows, will venting still be necessary for liquid to vapor media?
Perhaps not. It depends on the complexity of the system. We could take a look at it and perhaps design around it.
Is a flexible membrane ever used to accommodate the expansion or contraction of PCM rather than designing a sufficiently strong metallic enclosure?
Certainly. Bladders can be used to absorb some of that volume change, as well as bellows materials.
Are PCM materials available about room temperature with high latent energy, and are tables available?
There are several companies that provide paraffin PCMs in room temperature melt ranges. And many of them have pretty nice websites that list those as well as their thermal properties.
We have a question here. How does the latent heat of PCMs compare with that of the evaporation of water?
The evaporation of water is pretty hard to beat. So using the latent heat of vaporization is a very efficient means of storing energy, and you can store a lot of energy that way. But it can be a little bit more complicated when you want to use multiple cycles. Typically when we use the liquid to vapor transition, it's a one-time use, or the system needs to be recharged because you vent that vapor away.
What void fraction is used for the initial fill?
There are two parts to consider with that. One is the volume change between solid and liquid. The other part is what internal pressures can your system withstand. So as you reduce that void at the liquid state, you're going to see higher internal pressures. So if you have a very large heat sink with a very large fin pitch, you can withstand a smaller amount of pressure, meaning you need a larger void. Or conversely, if you have a very tight fin pitch and you have a very good pressure vessel, you can have a smaller void and handle higher pressure. Typically, they're in the maybe 7 to 12% void spacing.
Jens, this will be our last question. In your experience, what is the most efficient coolant that you've used with the PCM technology?
Again, water is very hard to beat, but in vapor compression systems, that's obviously not a good fluid to use. So in those systems, refrigerant is used, such as R134A.
Great. We'll end it there. That concludes today's webcast. Again, if we did not get a chance to answer your question today, our sponsors will do their best to address them after today's presentation. So our thanks to Brian Musica, Jens Wyant, and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.